Hello guys, welcome back to my channel Mason African Motives. Still working on engineering science info. So in this platform we shall actually work on statics, focusing on the question paper which was actually written in August 2019. So we have the question which is on question 5. We were given to study diagram 1 below to answer the questions. Alright, so this is the diagram that you are given. So as you can see guys, here we are given a distributed load which is of 20 kgs throughout the whole length. Okay, so then we have the supports here, the support A and B, and also to note this is 3 meters, so definitely in between here we have got 10 minus 3 which is 7 meters. But this is what is happening guys. This is a 20 kgs which is affecting the whole length of 10 meters. So what we need is to know like the force that we shall have per meter for this distributed load. So in order for us to find that, we shall simply find the force first, then we divide by the length. Okay, so which is the distance from A to B. So that will be force per meter. So the force in this case, we know that it's mg over the given length. So the mass in this case, that's 20 times g, which is 9,8 over the length of 10 meters. So this is actually going to give us 19,6. So we shall have 19,6, which is Newton per meter, because this is Newton, this is in meters, so it's Newton per meter. So which means this is actually a distributed load which is of 19,6 Newton per meter. All right, now for us to determine the margin of supports A and B, remember we have to take moments depending with the direction that you're going to take and so forth. So in this case, let's say we want to focus with A. On A, if you have to take moments about A, I want you to see something which is very, very important on A here. What we need is to know what is on the left side of A and what is on the right side of A with the 3 meters that we're having. So 19,6 Newton per meter is going to affect between these 3 meters. So it's 19,6 times 3 meters, which is going to give us something like 58,8 Newton here. Now separated between 3 meters, which is going to be 3 divided by 2, so that will be 1,5 there. You do the same for these 7 meters, so it's 19,6 times 7, which is going to give you 137,2 Newton. Now between 7 meters, so it will be between this point up to this point, which will be 3,5 meters up to 3,5 meters. So like what I'm saying is this guys, you are going to have something like this. All right, so we are saying from A to the left side of 8 there, we are 3 meters, so it's now 1,5 to the right side of A. We are going to have now between 3,5 meters. So now this is just something that you're supposed to have like to know in mind, not that you're supposed to redraw that. No, I'm just saying that you're supposed to visualize something like this in your mind. All right, so now let's take we are going to take first moments about A, then we move to B. All right, so let's take moments about A, which is as you can see, B is going to A in this direction, which is anti-clockwise. So we shall have the sum of anti-clockwise moments being equal to the sum of the clockwise moments, which is B back to A. It's a 7B. That's 7 times B, which is 7B. All right, do we have anything that is going in an anti-clockwise? Take note guys, this is anti-clockwise, this direction. So as you can see, it is the same thing as this 58,8 is going anti-clockwise, 20 is also going this direction anti-clockwise, but this is going this way, which is clockwise. This 132,7 is going this direction, which is clockwise. So we still have to add these two. All right, so as you can see, if you visualize this, it's going to be easier for you, because you're simply saying to the this part of anti-clockwise, we have got 58,8 with a distance of 1,5. All right, so we are going to add 58,8 multiplied by a distance of 1,5 plus, we said we still have another one of 20 back to A, which is 20 times 3. So that's 20 times 3. This is equivalent to what is on the clockwise, which is this way, 137,2 times a distance. Remember, it's in between 7, so this is 3,5. So you multiply by 3,5, so it's 137,2 times the distance of 3,5. So you have to combine everything, multiply these two and combine them. You're going to obtain something like 148,2 equal to, you combine this on the right side, which is going to give us 480,2. so definitely you have to transpose, which is going to subtract here. So 7b, you subtract 480,2 minus this, we are going to obtain 332. Divide by 7 both sides, so definitely your b, guys, is going to be 47,492,428. so it's going to be 429. That cannot change, which is in newtons. As you can see, all the other measurements that are in newtons, newton, so this one is going to be in newtons, like that. Okay, so this is our b, which is 47,429 newton, like that. Okay, so likewise we just do the same now, but taking our moments about b this time. So this is moments about b, so we are going to take moments about b this time. So as you can see, if we are to take moments about b, a is going this direction now, which is clockwise. All right, so a is going in a clockwise direction, so we shall have the sum of the clockwise moments being equal to the anti-clockwise moments there. All right, so let's take our a in a clockwise, which is going to be 7a, because there's a distance of 7 here. So we've got 7a. Do we have anything that is still in the clockwise from b here? As we can see, guys, we no longer have anything. All this is moving in an anti-clockwise, in an anti-clockwise. Remember, we said anti-clockwise is this direction, so we are going to take this force back to b here with a distance of 3,5. remember, so if you have this in mind, guys, it's going to help you. So it's 137,2 times 3,5, which is equal to, we are now on the anti-clockwise, 137,2 times 3,5. all right, plus we move on to, so in between here, anyways, this is what we're supposed to actually like do if it is to separate. Okay, I'm going to talk about that one later on. We could have just separated once. Anyways, let's just take this. We take this 58,8 back to b here, so this is 7 meters here, then plus 1,5, so it's 7 here plus 1,5, which is 8,5. so you're going to multiply, take note, this force here times this distance back to b, which is 7 plus this 1,5, which is 8,5. so it's going to be 58,8 times we said 8,5. all right, plus we still have another one, the last one, which is 20 here back to b, so it's 10 meters, because it's 3 plus 7, which is 10, so it's 20 times 10. all right, so like I said, I could have done this in another way. Let me show you later on. So just combine these two, you are going to obtain 1,180 divided by 7 by 7. So a is going to be 1,868, comma, this is going to be 57142, and so forth. So it's going to be 142 newton. So that's our a, which is 168, 57. This is 142. No, 57. This is 57142, which is going to give us 168, 571. Yes, in newton, like that. Okay, so this is 168, 571. Take note, guys, for that. Sorry. So like I said, I could have done this. Take a look on the distributed load, how I took it like this one and this one. We could have just taken this way to say that this 19,6 is separated in between what? In between 10 meters, because you are talking of B, so A is not important for that moment. So you distribute, you are going to do in between, so you're going to take it as a point load for these 10 meters. All right, so if you are to take it for these 10 meters, it's going to be 19,6 times 10 meters, which is 196. So it will be like this, in between like this, so it will be 196 newton like this. Then in between, now since you have taken between 10 meters, it is going to be 5 meters from this point up to B. It is going to be 5 meters. So this could have been taken like this. We could have been taken it like 7A is equal to instead of taking this 137, now we are going to take it as 196 times 5, because we have taken it in between, so it's now between 5 meters, so it's 196 times 5 like this, plus the last one, which is 20, back to this one, which is 20 times 10, which is plus 20 times 10. So still we are supposed to obtain the same answer from this. So this is going to give us 7A. You multiply these together, that's 1180, divide by 7. So as you can see, you shall obtain the same value of A. So you could have taken it in a halfway like that, it was going to be the same, or you could have just taken it from the way that we have taken, since we said we could have separated in between like this because of A. But for A there was no option, because for A you must know what is on the left side of A and what is on the right of side of A. So you have this option, that is what you have for A. All right, so that's what we had. Anyways, we're going to keep this aside and see the other question what you're given. On 5.1, to draw a neat detailed shear force diagram. That's just 2 marks for that. Okay, so in this case I'm just going to represent what you are supposed to know, how it is supposed to actually look like. Okay, let me take this one, guys. Let me use this one. All right, so this is a shear force diagram for us. As we know, guys, the shear force diagram, we shall start at 0, then we work with the direction as we are given, so that's at 0 there. So I'm going to work with this diagram here, and it's gonna be easier for us to understand what's happening here. All right, so this is the first point, which is at 20 here, and it's a point load, is going downwards. So this one is going to be a negative force, is going down, so it's going to be 0 minus 20. So 0 minus 20, that's minus 20. So this one is going direct downwards up to minus 20. Okay, so let's just say this is our minus 20 here. All right, let's just say this is our minus 20 newton here. All right, this is minus 20, guys. I hope it's clear, even though it's not that much clear. All right, anyways, then between this point that I'm calling C here and this point B and this point A, sorry, for me to move from this C to A, there is a distributed load here, which is this one that we talked about of 19,6 newton per meter times 3 meters, which gave us 58,8. So we shall have to consider this distributed load, and as we know that a distributed load is supposed to be a slanting line like this, so we shall subtract 15,8 for a distributed load. Okay, so if we subtract from minus 20, because we are now at minus 20, so if we subtract 58,8 for the distributed load, we shall remain at minus 78,8 newton. So this must go up to minus 78,8, which is a slanted like this, somewhere like this, up to minus 78,8 newton like this. All right, then we move on. We are now at A here, and at A there is a support, and we know that a support is a positive because it's going up. So to this value that we were at now, we are going to add at minus 78.8, we are going to add our support, which is 168.57, which is going to give us something like 87, something like that, 89, not 87, 89.771. So this is a positive, so it's going up direct, and this is it's a support, so it's going direct up. So you draw using your ruler, guys, up direct there. So I don't know, just somewhere here, direct. This one is a vertical line. All right, up to 87. This is 89, sorry, 89.771. So that's what you do, guys, throughout, and so on and so on. Okay, so that's it. So the same thing here. Take note, this one we are not going to consider as a 190. Suppose this one was not there, because we are talking of this one in red. This one, remember, this one I used it for that when we wanted to calculate this support here. So we are not going to work with this 196. This one we are working with this 58.8 and this 137.2, the ones that are separating the diagram. Okay, so this is it. From A here up to B, this is what is happening. From A up to B, there is a distributed load all throughout. So we are going to subtract 137.2 for the distributed at this number here, which is 89.771, because that is where we are now, minus 137.2. So this is going to end up reaching up to minus 47.429 Newton. That is where it is going to be, and this is a distributed load. So this one is going to slant up to minus 47, which is somewhere, this is minus 20. Remember, this is minus 20, so minus 47 might be in between, let's say in between these two, somewhere here, but it is going to be like this because it's a distributed load up to a point somewhere there, because it's just supposed to be minus 20, minus 40 something, then minus 70, whatever that you have there. So this is your minus 47, 429 there, 429 Newton. That is where we are now. All right, now at that point B, we have got a support, and we said a support, it's a positive and it's going upwards. So we are going to add minus 47.429 plus the support that we are having, which is 47.429. So if we add these two, definitely we are going to obtain 0 Newton. That is, now we are back to the point at 0 there, but this is a support and it's going up. So this one is a vertical line direct up to 0, a vertical line direct up to 0 there, Newton. So we are now back to where we started, so which means it's truly in equilibrium, because it is giving us a closed figure like that. So this is supposed to be a straight line. Okay, draw with your ruler, something like that. So here I'm just showing you how it is supposed to look like, and how you do everything there, but that is the idea there. All right, so that's what we had. So let's see another question, which was now to determine the bending moments at the principal point. Okay, so we need the bending moments. Okay, so what is going to happen is that we are going to have the bending moment at this. So here I have indicated this point C. So we're going to have, because already we were given A and B, so I've indicated this one as an extra point C at this point. So we've got here bending moment at C, bending moment at A, and then bending moment at what? At B. But this is what is going to happen. If you are to cross check on our shear force diagram there is something that is happening where we know that whenever a distributed load is going to affect, like when we have a distributed load, whenever there's like here, this is for a distributed load, and this distributed load is crossing the horizontal line at this point. So whenever it crosses the horizontal line, it means we are going to have a maximum bending moment there, which is we are going to have the maximum value for that bending, which is when you are to draw. So we are having an extra point where you're having the maximum moment there. So what is happening is that we need to know the distance that is going, because it's in between. We don't know it's between these three or here, so we just know that there is a point that we are going to have that we do not know where actually it is located. So this point we shall just call it E. We shall it's what we now at D, so I shall just call it D because we've got C now, then D. So I shall talk about this one, which is a certain distance back to this point. Let's just call that distance X or Y, whatever, so you can even call this the distance X. So I shall talk about this one later on. Now let's start with the obvious and definite bending moments at C, at A, and at B. All right, so this is what we have. So here I shall talk about this one later on. So that is what you're going to have, guys. This is 5.13. So we've got bending moment at C. So at C, guys, as you can see, C bending moment, remember, it's force that you're going to have by this, and this is negative 20 because it's going down, but there is no distance that it was moved, so the distance is 0 there. So it's minus 20 multiplied by 0, which is going to give us what? Which is going to give us, this is Newton and this is meters, so it's going to give us 0 Newton meter. That is our bending moment, and this one we have taken it from what? From the left. All right, anyways, let's move on to the bending moment at what? At A, which is at this support at A. So at A, this is what is going to happen. There's a distance of 3 meters to A. So this is what we have at A, guys. We have got 20, this one, which is minus 20 times 3. All right. Also, we have got this point that we are going to have between A, because remember we have got 19.6 Newton per meter that we have. So that means we are going to subtract the force that we are going to have per meter times the distance between what? Between 1.5, because here we are having 1.5. Take note that, guys, what I'm talking about there. So that is what you're going to, let me try to adjust this side so that I can put it nicer. All right, I think it's clear. So if you are to take this is going to be a negative from 20 because it's going down. 58.8, which is the one from 19.6, is also going down. So this is going to be negative 20. But what is the distance now between to A? So there's a distance of 3 meters. So it's times 3. All right, minus, this is still going down. 58.8 is going down, but there's a distance of 1.5. Now remember, it was distributed between 3 meters, so now it's 1.5. All right, so it's going to be 58.8 times 1.5, which is the distance between. All right, so this is going to give us something like negative 148.2. all right, Newton meter. So this one we have taken it from the left, so we are done at this point at A. Then the last one, which is not the last one actually, but according to the direct ones, which is at B. So this one B, we just have the force and there's a distance of 0 there. So we've got the bending moment at B, which is a force of 47.429 times 0 there, which is going to give us 0 Newton meter. So this one I've taken it from what? From the right. So take note here, from the right there's no distance that is in between, so that one is going to be a 0 like that. All right, so now with these values, we talked about the point E. Remember that we say there's a certain distance in between that to the point C, which is X. So we do not know about this distance. We do not know about this distance. So okay, let me just give you an idea of what is happening there. Okay, this is where we are having our minus 20. I just want you to visualize what I'm talking about here. This is what is happening like this. That is where we had our 20 Newton here previously. That is what we had. Then we are saying we do not know the distance that is going to be taken up to the point E. So we shall just say this is where we are having our E here, and there's a distance of what, of x meters in between. But what we know is that we have given a distributed load in between. This one is not going to change. It is going to remain as it is, as 19.6 Newton per meter. We are no longer working with this 58 because this one was in between 3 meters. This time we do not know the distance, but only the thing that we know is that there is 19.6 Newton meter here. So how can we calculate now the value of x? How can we have the value of x? So this is the question. All right. So as we can see, we are given a downward force, this one. So which means we can play around with something of this nature to say that, let's say we know that the distance is there. Let's say we know that the distance is there here, which means we were going to have something like this. If we know the distance, we are going to have something like this. We are going to divide into 2 because, okay, this is where we are having our distributed load here. So let's say the distance is there and we know that distance. This is what was going to happen. You were going to multiply 19.6 Newton meter, this one. Okay, guys, let me take you back to what you used to, like this one. You knew that the distance was 7 Newton meters and the force per meter was 19.6. So you multiplied 19.6 times 7 and obtained 137.2, which you drew like a concentrated, like that, a point load. So it is the same thing, though we do not know the distance. So we shall just make an assumption to say, okay, we have the distance as x, so which means the force here is going, remember, the force is equivalent to the force per meter times the distance, which is in meters. So the force per meter, 19.6 Newton per meter, times the distance of x meters is going to give us the force, which is going to cancel this one, which is 196 times x, which is x in Newton. So which means there is a force here in terms of x, which is 19.6 x Newton going downwards like that, if it is like this now. So now we can formulate an equation to calculate the value of x. Why? Because we know that the sum of upward forces is equal to the sum of what? Of the downward forces. All right, that's what we know. If we are working with upward forces, they're equal to the downward. All right, so in this case, this distance, also the other thing that we are supposed to consider also is that, let me show you from the diagram here, where we are having this line crossing the horizontal line, this horizontal line. This point here is actually after the support which was at A. This support here which was at A, this point is after, which means the support at A is supposed to be involved on the diagram. So which means there is a support A on the diagram of 168.571 Newton, which is somewhere, let's just say it's here, we don't know actually where it is, but we just know that there's a support here of 168.571 Newton. So this is the one that is going to represent your F up, the one that is going upward, which is 168.571, which is equal to the sum of the force which are going downwards, which means we are talking about this 20, which is going downwards. So it's 20 plus 19.6x. Remember, this force is written in terms of x as 19.6x. So you formulated an equation where you can calculate x, which is the distance between the points up to E. So just transpose this to the side, guys. As you can see, subtract there, is going to give you 148. If you subtract 20, it's going to be 148.571, which is equal to 19.6x. Divide by 19.6 both sides, so your x is going to be something like 7.580155, which is 0 like that. 155, so it's gonna be like this in meters. So this is x, guys, which is the distance that we needed here from this point up to this point here. There is a distance which is 7,58 meters, just the same as 7,580 there. So once this distance is there, then it's now easier for us to have what? To have the bending moments at D, because the major thing that we're doing this is so that we can have the bending moment at the point. Oh, I wrote it as E now. Okay, anyways, it's fine. Let's continue to use it as E, but it was D. So we now wrote it as E. So the bending moment at E now we are going to have, remember, there is a support that is going upwards there. All right. So, but in this case, this support is 160, 8,571. This one we know the distance. Okay, how are we going to find the distance for this support? Because we need to know the distance. Okay, this is it, guys. There's something that is actually missing that we need. I don't know how it is going to be clear enough now on this diagram, but I hope you're going to see it. This was happening. Remember, this is the support A, and we know the distance before on the diagram there, the distance that was for A. We know this one from the diagram. Remember, from C up to A, the distance, this one we already know that this one is what? Is 3. So this one we already know that this distance here is what? Is 3 meters. So to know the distance that you're going to take now from what? From the support A back to E here, you are going to subtract, because from this point to this point it's 7,58. So you're going to subtract 7,58 minus 3, so that you're going to remain with 4,58 meters. So now you know the distance that from this support A to E there is what? 5,48 meters. All right, so this is what you're going to have now as a positive. So it's positive 16. This one is a support, so it's going to be a positive 168, 571 times a distance which you said 4,58. Remember, we want the distance back to the point E. That is why we have to subtract this 3 which is on this side. All right, we are done with this one. We go on to this 20 here. 20 is a negative because it's going downwards, so we are going to subtract. So it's minus 20 times, as you can see, from 20 up to E is totally the whole distance that we calculated, this one of 7,58. So you're going to multiply by 7,58. All right, we move on, guys. Take note, there is a distributed load, this one that we distribute between these x meters, and we said it's 19,6x. So it is going to be 19,6x. Then there is a distance that is in between now for this distance that we calculated. Remember, the distance is 7,58. So you have to divide by 2. Okay, so if we divide by 2, we are going to obtain something like 3,79 here. So it's 3,79 meters. 3,79 meters. So that means in order for us to have this force times distance, remember we said our force is 19x, as we said 19x, but we've calculated x and we obtained 7,58. So this is what is going to happen. We are going to subtract, remember it's force times distance, so it's 19,6x, which is 19,6 times x, which is the one that we calculated, which is 7,58. So it's 7,58. So this is just our force, but we need the distance between that force back to what? To E, which is 3,79, because it was distributed between 7,58 and we divided by 2 and we obtained 3,79. So this is going to be multiplied to 3,79. So that is what you're going to have at the end. So take note, guys, that is what you're going to have at end, and this is now our bending moment at A, which is going to give us something like 57, something like that, 57 comma 3824. So this is be 24 and something, and it will be 382 because it will be 4 6, and that 4 cannot change 2, so it will be 2 like this, and this will be Newton meter. So that's what we are having, guys, as the bending moment at what, at the point E. So like I said, that's what we need. So the question was for us to calculate the bending moments, guys. So this one, be very, very careful how you calculate it, and there are so many ways and methods. So as we shall be working on different questions, I shall also be explaining those different methods, but there are ways that you could have done also, so that it can be easier. So we shall see as we move on, guys, but for the meantime, that's what we have. Just try and work with that as much as you can. All right, anyways, let's see the other question now, which was a continuation on 5.14 to draw a detailed bending moment diagram. So this one is a bending moment diagram, so definitely we have to work with our bending moments, and also an idea of the diagram also that we are working with. Okay, so this is it, guys. We shall have something like this for the bending moments. This is 5.14. All right, so this is 5.14. All right, so this is it, guys. We shall definitely have to start at 0 there, which is Newton meter, and this is happening at minus 20 there. We have got bending moment at what, at C, which is at 0, this one. Then we move on to the bending moment at A, but there's a distributed for us to go to that bending moment at A, which is a bending moment at A, which is a negative. So we shall have a distributed up to negative 148. So remember, a distributed is supposed to be a curve like, so it's supposed to be a curve like, all right, something like this, up to negative 148.2 Newton meter. So this is actually at what, at A. Then we move on to B, which is the bending moment. So guys, direct at A, then to B, which is at 0, and it's a distributed, this one. But remember, there is a bending moment at E, which is a positive at 50, whatever that we had there. So definitely for this one to go to 0 there, it must pass that. It's a distributed, this one, so it must go in a distributed manner until it goes back to 0 there, something like that, which is actually 0 Newton meter, but it has to pass the way that one was a maximum positive at 57.382 Newton meter, which is the bending. Hey, this is bending moment. Now it's BBE, guys. Bending moment at E, which is the point E, and this is the point B, the last point, which was on the on our graph, which was the point B, not D. So it's all about the it's the distributed load, guys. So guys, distributed load, I think everything is clear. As long you've got your bending moments, then the diagram is gonna be very, very easier. So what I encourage you is to revise on bending moments, guys. You need to revise on bending moments there. That is what is very, very important for you, to revise on bending moments. I think it's gonna be very, very much good for us. Okay, then on the other part, which is on 5.2 there, we had a question which had actually had 5 marks to make it a 15, to study the diagram 2 below to determine the position of the distance of the lamina from AB, that is the y value. So AB, so which means we shall calculate the y value. The hole in a triangle has a diameter of 20 millimeters. So there is a hole inside, which is this the one that we are given a circle cross section, which is a diameter of 20 millimeters. Then also, what are we given? We are also given that h is 77. So h, which is the height of the triangle, this one, as you can see from this point up to this point here, that is the height of what, of a triangle. So this is your edge, the height of the triangle, this one, that is the one that you are given. So we have also the value of h, which is 77,942 millimeters, like that. All right, so this is what you're going to have, guys, in an easier way, because the question is for us to calculate the y value, and we actually know that in order for us to calculate the y value, there actually are different methods that you're going to work with. So I'm going to explain two methods in different ways, actually in another class, so that we can actually understand what is happening. Okay, the first method that you're going to work with is to have something like this, where you are just working with in this case you are just working with area in the centroid. Remember, this diagram can be subdivided into two, where you will be working with the because, guys, this is the distance from the center of lamina. Okay, so when you are given that you are working with what, with the centroid, so it uses area. Gravity is the one that uses volume. All right, and this is the y value that you are working with. So for you to have the y value, you are going to take y values. So in this case you take y values in this case. Okay, so like I said, I have two methods, so I'm going to explain the first one in this class, then I will explain in another way again. So what you're going to do, you're going to take the area moments in this case about the x-axis, which means you're taking area moment about the x-axis in order for us to have the y value. So which means y value, you're going to take moment about the x-axis. All right, now this is what you're going to have. Okay, we have got your shape, which is the area, then the centroid. Like I said, we've got two methods. This first one, you just have to make a simpler diagram. So your triangle in this case is the one that you're having as the major diagram, then a circle inside. So the total area is going to be the area of a triangle minus the area of what, the area of a circle. We'll talk about that one, but anyways, we know that the area of a triangle, guys, is equivalent to half base times perpendicular height. So it's half times the base, which is the base we are given from this point A up to B. It's 90 millimeters. Then the height, you are given that height there. So it's half of 90 multiplied by 77,942. So let's say in a case that this height was not given, how are you going to calculate it? You are going to apply Pythagoras theorem. Since this is a right angle triangle, you apply Pythagoras theorem to calculate this height. Let's say they didn't give you, but in this case already we are given. So you're going to obtain an area of 3507,39 square millimeters. Okay, we are done with the area. Then the centroid, since we are focusing with the y value, you are going to take the value of y, and we know that for the centroid, it's for a triangle, it's a third base, a third height, like this. So this is the value for x and this is for y. So y is equal to a third times the what, the height, not base, because we need the value of y. So it's a third of the height, and our height is that value that we are given, 77, whatever that you have, 77,942, which is going to give us something like 25,981. All right, this is in millimeters. So this is the value of y for the triangle. Then we move on to the circle. You know that area of a circle is pi d squared over 4. All right, which is going to be pi times d squared. Okay, the diameter we are given 20 millimeters, so it's 20 millimeters over 4. So this is going to give us something like 100 pi square millimeters. So this is 18, or you can write it as a decimal, which is 314,159. Okay, this is our area. Then definitely we have our centroid here, and it's a circle. So for a circle, remember y is equal to the radius. So, and the radius is diameter over 2, so which is actually diameter over what, over 2, that's the radius. But now this is what we have. This is your radius for the value of y. But take note, there is a distance between the radius, this one, and the ground, because you are now considering the value of y. So there is a 45 millimeter which is to be included as a height, this one, plus that radius. So on your radius you are going to add 45 millimeters. So this is going to be radius, which is diameter over 2, 20 over 2, which is 10 millimeters. So we are going to have 10 millimeters plus 45, 10 plus 45, which is a 55 millimeters. This is millimeters, guys. All right, so that's what we have there. Now that we have this, what is it going to help us? How is it going to help us? Okay, remember I said you're going to take moments about the what? About the x-axis. So for you to have the moments about the axis, that is for you to have the value of y. So it depends like which method. Okay, let me just explain both of them in this video at once. Okay, the first method, okay, this one we have used it. You are going to use moments. Okay, so you're going to use moments to say we said we are going to take moments about x-axis. This is moments about x-axis. All right, so if we are to take the moment about the x-axis, what you are going to do is that you are going to calculate the total moment, all right, which is equivalent to the sum of separate parts. So you're going to separate the parts, but this sum of the separate parts, you have to consider the diagram is if there is a hole, you subtract, like that one, there is a hole, you subtract this one a hole. All right, that is the separate part. So the total moment also you subtract the area, because remember the total moment is just the total area times the value of y that we are talking about, which is the one that we want to calculate, which is equal to the sum of separate parts. We are going to have the area of a triangle and the area of what? The area of a circle, but this one we are going to subtract it. So it's going to be area of a triangle times the distance of y for that one, minus the area of a circle times the distance of y. So this one is the one that we are given. Let's just say y1, y2, because if we say y, it will be like this one. No, just y1, this was that we determined. So let's just say y1 and this is y2. All right, so that's it. Area times the distance, just like that. So like I said, this total area now is going to be area of a triangle minus area of a circle. That is what you're having, because there is a triangle, then it's a hole that you're having. There's a hole there. So whenever you're given a hole like this, you subtract that hole. Okay, you remove the hole. So that's what you're going to have. So you're going to formulate an equation, definitely, because the area of a triangle, you're going to say this one minus this one, which is 3507,39 minus the area of a circle, because it's inside, which is 314,159. Then definitely your answer, you're going to multiply by the distance that you want to calculate y there. All right, which is going to give us here, you are going to calculate, you are going to subtract y because there's a hole. If it was a consideration like this, you have got something like this, then okay, you are going to add, because these ones is separate, they are separated. This one is not a hole. A hole is something that is inside a shape. You subtract. Okay, so here you subtract, here you add. That is what is happening. So that is area of a triangle, which is the area of a triangle, this one. We just take as it is, which is 25,981 times, sorry guys, I took, okay, anyways, this is the area of a triangle times it's we're going to multiply these two. It was supposed to be this number times this number. Anyways, multiply them. So we are going to multiply to the area of a triangle, which is 3507,39. So that's our area, our moment there, minus the one of a circle, the one that you want to remove, because we said we are going to remove a circle in this case. So let's remove a circle, which is a circle area times the distance, which is the area of 314,159 times the distance of 55 millimeters, like that. So here, combining these two, you're going to obtain something like 3 that's going to be 3193 comma 231, all right, times y in this case. Then here you combine these two minus these two, so you're going to obtain 73846 comma 74. So definitely you have to divide by this value here, divide by that value, this one here. So y is going to be 23,126, something like that, which is in millimeters. So that is the value of y. So like I said, to calculate the value of y, you're going to consider moments about the x-axis. If you want to calculate the other one, you're going to consider moments about the y. So it's a vice versa like that you're having. So now my question is, what if we could have, now I was thinking of separating this, but let me just talk about it now so that we just complete these guys at once. What if I had to separate my diagram like this? What if I had to separate my diagram? I don't know if okay, it's clear. That's it there. So if I was to separate my diagram like this, I was going to have the shape, take note, the shape, the area, the centroid, then the area moment. So this one, you are going to calculate the area moment on the diagram at once, which is area moment is the area times the centroid. So this portion here is just the same as what we did. You just extend this part. So here we are not going to waste much time. This is what you're going to do. We already calculated the area of a triangle, the centroid, and so forth. So I'm just going to fill those values here, so that so it's going to be 3507 comma 39, just like what you did, guys. You just do it at once. The centroid, we have calculated it 25,981 again millimeters. For a circle, the same thing. This one is the same thing, guys. All right, the centroid was 55 millimeters, which is the value of y here. All right, so from this formula, it's saying AC, that is your area moment, which is area times the centroid. So you multiply these two. So here your AC is going to be, you multiply these two. So if you multiply these two, you are going to obtain something like 91125 comma 5, which is a cubic millimeters. This one, because it's area moment. Take note, it's square millimeter times the square meter, so it's going to be cubic. It's square millimeter times length, which is a square, which is centimeter, so it's going to be cubic millimeters. Okay, you move on to AC for the circle, which is you multiply this one and this one, area times C, A times C, you multiply these two. So like I said, guys, these ones we already calculated them before. So this is going to give you, now I used another value there, so you're going to obtain whatever that value that is, which is 55,000 pi there. So as a decimal, I don't know, you just take the value that is equivalent to 55,000 pi there. That is one that you're going to take anyways. So that is what you're going to have as your area moment here. Now this is so this one I'm taking from that. Remember my area here, I had two areas here. I had this one 100 pi or this one. So you just take this one or this one. So here I use this one, or you just use this decimal. So in fact, on your calculator, just 55,500 pi is equal to, then you change to decimal. Okay, so you, as you can see, it's a repetition, because this one we calculated it, but we just did it in a hidden way from that manner. All right, so now this is it, guys. This was just a hidden way. Now we are going to come to this side now to say this is our total area now. So we are saying there is a triangle and there's a circle. So we're going to calculate the total area, the sum of areas. So since there is a hole, like what we're saying, that whenever there is a hole, you have to subtract here, like what you're given. So it's, in this case, it's area of a triangle minus the area of a circle. So you subtract the two areas, which is this one. You can just say this is our first area, our second area, so it's going to be A1 minus A2, which is the first area, this one minus this one. So when you subtract this, I'm not going to write it, but I'm just going to write you the answer here. You're going to obtain something like 3193, 231, which is a square millimeters. Okay, here there's nothing, just leave it like that. You move on to this value here, okay, which is for the area moment. So you shall have also the sum for the area moment, which is the area times the centroid, which is you subtract, since there was a hole. So now you are subtracting because you already calculated these moments separately. So you're going to subtract this value minus this value. You're going to obtain something like 73846 740, which is cubic millimeters, because this is area moment now, so it's cubic millimeters. All right, so this is it, guys. You have the sum of the area moments about the x-axis, and also you have the sum of area. So the y ordinate or the y value that we want to calculate in this case is going to be the area moment about the x-axis over the area. So we are simply saying the sum of area moment over the sum of area. That is your y value. Simple like that. When you understand the diagram, it can be much easier. So like I said, this is a repetition. This one, it's a repetition from the first diagram. It's not changing what we did on the first diagram. This one, you do the same as it is. You just repeat the same as it is on this diagram, just as it is. But the only thing that you're going to add is the area moment and also the sum of the areas, like that. Okay, so now you're going to substitute the area moment, which is this value 73846 740, which is cubic millimeters over the area. Remember, area is square millimeters, which is this area of 3193,231, which is in square millimeters. So as you can see, square millimeters and cubic millimeters, you are going to have your answer in millimeters. Your y is going to be 23,126, yeah, something like that, if you round off properly, in millimeters. So as you can see, we are obtaining the same thing. So it depends with how you are going to take or represent your diagram. Okay, but that's it, guys, on this question, which was actually on moments. So as you can see, it's best that you understand the basic of the question that you are given, how it is illustrated. So from the illustrations that you are having, that's how you just attempt the question. So that was it, guys, from this question paper from August 2019, where we are given a condition for the beam, and also working with calculating the centroids there, which is working with area moments. So we shall hope again to have different questions that are going to give us different calculations, especially on moments. That is the major part that I want us to actually understand much better, because it can save you much time in exam if you know this part. So actually, when you know the basics, all these diagrams, you can even visualize them by not even redrawing like what we're doing, just to visualize the diagram. Then you'll be able to do or to answer any question. So that's it, guys, for Mason African Motives, working on engineering science and for working on question papers, but revising a lot from those questions. It's not just about a question paper, it's also about a topic. We are talking about the whole topic at once. So this is supposed to be something that is supposed to be utilized, because you're talking of a topic at once, not just a question paper. So we shall have another part again, or another topic. So if you are new, guys, you can consider being part of the family Mason African Motives by subscribing, so that you won't miss any of the classes that we shall be having from Mason African Motives, working on engineering science and 4. Till we meet again.